Okay, so welcome to the part 3. So in the last part we saw that if this is the optimization problem, uh, minimize fx subject to j of x less than equal to 0 for all j from 1 to l, and x belongs to Rn. Then the capital X is the feasible set, uh, which contains all the x which belongs to this constraint set. J equals to 1 to L, right? So suppose my local minima x star, it should lie in this feasible set capital X. Then we saw last time that if this is a local minima, this implies that f bar of x star intersection d bar of x star is a null set, right? So intersection of these two sets is a null set, which basically implies that my set of all d vectors uh, such that gradient of hj transpose d is strictly less than 0 for all j which belongs to the active set. Of x star, right? And intersection of the descent directions, which basically gives me set of vectors such that gradient of fx star transpose d is less than 0, and the intersection of both of them is a null set. Fine. So let us just combine uh, both these coefficients of d into a matrix called, say, capital A, right? And this matrix will contain rows of gradient of fx star and gradient of hjx star, where j belongs to the active set of x star. Fine. And obviously the number of rows in this will be uh, 1 plus the cardinality of active set of x star times n, right? This is the dimension of the matrix. So so suppose if we want to, so suppose if x star is a local minima, this implies that uh, the set of all the vectors d which satisfy this condition, a into d, uh, a times d less than 0, is also a null set, right? So basically what we did was we just combined both these conditions to find a to find the to combine basically the coefficients of d, and we compiled them into matrix A, and we are just saying that if these two conditions are put together and we find a d, then that particular set will be a null set. Okay, so now if we want to solve for an optimal x star, basically if we want to find this local minima, we'll have to look at a set of lemma, a lemma called Farkas lemma actually. So again, as I'm doing in this particular lecture, that I'm just stating the lemmas without any proofs. So I'll do the same with the Farkas lemma also. However, I'll link down the proof of the Farkas lemma in the description below for people want to who are curious and just want to go through the proof ones. So let's see what Farkas lemma says. So Farkas lemma says that suppose if I have a matrix A which is of the dimension R m cross n, and there is a vector C which is a n dimensional vector, then only one of the following conditions are true. Then only one of the following conditions are true. So what are these conditions? First of all, Ax less than 0 and C transpose X greater than 0 for some X belongs to, for some vector X and which is n dimensional, or the other condition is true which is A transpose Y equals to C, where Y is a m dimensional vector. So and comma some non-zero vector Y, right? So this is the lemma. So it states that suppose I have this matrix A and a vector C, then only one of these conditions are true. So it can never happen that both of them are true simultaneously. Okay, so I'll link down the proof of this lemma. So if you're interested in knowing why this is true, can actually go through that lecture. So that lecture is taken by my friend and my colleague Aman Singh. Uh, so it's around 1.5 hours long video, and explaining the proof of Farkas lemma in quite detail. So if you want, you can actually see that video. Uh, okay, so now I'll move to one of the corollaries of Farkas lemma. So corollary of Farkas lemma. So let A is a n cross m matrix, right? Then exactly one of the following conditions are true. Following conditions are true. So the first one is either Ax is less than 0 for some x, or A transpose Y equals to 0 and Y is greater than 0 for some non-zero Y. Belongs to Rm. So you can actually see the similarities between the corollary and the actual lemma. So as you can see, we just replaced c by a zero vector, and that is how we arrived at this corollary. Okay, so now that we have stated the Farkas lemma and its corollary, let's now use this to derive a condition on the local minima thing that we that we came to. So we'll use this condition. Okay, so as you might have guessed, uh, suppose if my x is a local minima, x star is a local minima, which means the set of all d's where a of d is less than 0 is phi is basically null set. So by Farkas lemma, we'll have, since this is not true, so basically this particular condition is not true. So I think I'll show this is not true. So obviously this condition is true, because we know that the set of all d's where this condition is is valid is a null set. So obviously this other condition is true. Okay, so this means that my A transpose y equals to 0 and y is greater than equal to 0 or some non-zero y. So let me take a vector, say lambda 0, lambda 1 up to so what I'll do is basically I'll use since this is to be multiplied by a, right? So I'll just use the subscript of gradient of hj, that is basically j, to define my lambdas here. So the coefficient of gradient of f in this case will be lambda 0, and the ones of the coefficients of gradient of hj will be lambda j. Okay, so this is what I'm choosing my y as, right? So for my y to be non-zero, I have to have at least one of these lambdas to be non-zero, right? And all the lambdas have to be greater than or equal to 0, right? So let's write this condition. So basically lambda 0 times gradient of f of x star plus summation of lambda j gradient of hj x star, where j belongs to the active set of x star. Fine, and this is equal to 0. Fine, and so since this is equal to 0, we need to find a condition such that we ensure that like at the same time all the lambdas are not 0. So basically lambda 0 and lambda j's are all not 0 at the same time. or I'll just say non-zero at the same time. Fine. So what I'll do is I just want that my gradient of edges are linearly independent at any point. So what I'll do is I'll say that let me define a term called regular point. So regular point is a point. So my x star is said to be a regular point. Regular point if all the gradient vectors like gradient vectors, that is basically hj, gradient of hj x star, are linearly independent. Okay, so if my x star is a regular point, this implies that my lambda 0 is not equal to 0, right? Because all these gradients are linearly independent, and for my so if you want that this particular term is 0, then one of the vectors have to be positive, uh, so that we don't have so that we don't really come at this condition where all the lambdas are 0. Okay, so if my x star is a regular point, then my lambda 0 is non-zero. Okay, so what I can do is, if my lambda 0 is not equal to 0, I'll actually take divide the entire equation by lambda 0, right? And then I can actually just replace this particular equation by this condition, gradient of x star plus summation of lambda j. I'll say that my lambda bar j equals to lambda j by lambda 0. Okay, so lambda bar j into gradient of hj x star equals to 0, right? And then I can say that my lambda j uh, is greater than equal to 0, right? And what I can say is that like this belongs to my active set of x star, right? This is my final condition in a lambda bar, sorry. So now let's see, like if I for suppose I not belonging to the active set of x star, what can we say? What we can do is basically we can still include these conditions, those gradients which are not active set, but we then just say that my lambda bar of I equals to 0, right? So suppose if I put my lambda I 0, then in this particular equation summation of lambda I bar and gradient of hi bar, sorry, hi uh, is equal to 0 because my lambda is equals to 0, right? So what I can do is uh, I can actually include all the all the points, all the constraints basically, right? I don't necessarily just have to include the active set, but we can actually come to a final condition in which we account for the uh, we account not only for the active sets, but we can actually generalize it for the for all the constraints in a way. So I can actually write this as fx star plus summation of lambda I. Let's write I, maybe we'll use something else. We can write lambda k gradient of x x star equals to 0 for all k belongs to, so sorry, k belongs to the entire constraint set till L. Okay, and now what I say is that my lambda j, sorry, lambda k hk of x star equals to 0, right, for all these case. So suppose if my k belongs to active set of x star, then uh, for if let's suppose it's not equal to first, since it is easy, as you saw here that uh, sorry as you saw here that, so for k not belonging to the active set, lambda is equal to 0, so this condition is automatically true, right? Because uh, lambda is 0 in this case, lambda k is 0 in this case, and in the case where k belongs to the active set, this is true because my h of k equals to 0, because active set means what? Active set means the set of all the points, where was it, yeah, set of all the points where my constraint is 0, right? So basically in either of the cases this particular condition is true, right? And the other condition is that all the lambda k's are greater than or equal to 0, because like for the case where uh, for k which does not belong to active set, lambda k is 0, and where k belongs to the active set, lambda k is greater than or equal to 0. So basically we can generalize these conditions for all the constraints basically, but we still need to keep the track of what all constraints are active and what all are not. Okay, we'll see all these things in much more detail. So we have defined now like make sure that you like properly understand this. So till this particular time we were just considering all the lambdas which belong to the active set, and now here we are considering all the k's which are all the k's in the constraint, in the constraint set actually. Okay, so this basically forms my KKT conditions, or Karun Koshtakar conditions, as the names of the people who derived these conditions. So Karush Kuntakar, basically taking the first letter of each scientist's name, KKT conditions. So Karush and Kuntakar basically came to these conditions independently. So everyone was given the credit, and that is why we call it KKT conditions for short. This is like these conditions are quite famous for solving constraint optimization. And whenever I mention KKT conditions in this course, I refer to the conditions that uh, I'll describe now, or what we have derived till now basically, right? So let me just formally uh, state the conditions again. So for the constraint optimization problem, minimizing fx subject to conditions of hj(x) less than equal to 0 for all j belongs to 1 till L, and x belongs to Rn. Okay, and again, capital X is the set of if is the feasible set. Right, and if so, suppose these are my first order KKT conditions, KKT necessary conditions. These are basically first order because we just taken first order derivative. So it states that if x star belongs to the constraint set is a local minima and a regular point. So a regular point, as I told above, is a point where all the gradient vectors are basically are linearly independent. So if my x star is a local minima and also a regular point, then there exists a unique vector lambda, I call it lambda star, such that like the lambda star is basically lambda 1 star, lambda 2 star till lambda L star. Such that gradient of fx star plus summation of hj of x star. Sorry, it should be j, I think. J varies from 1 to L equals to 0, right? And lambda star j hj of x equals to 0, and lambda j star is greater than equal to 0 for all j belongs to 1 till L. Okay, so basically what we what we'll call that KKT, like that the set of these two vectors, basically x star and lambda star, are called the KKT points. Fine, where x star belongs to the constraint set and lambda star is greater than equal to 0. So and we call that this function, basically what we do is we actually we take the gradients common and we call the function L of x comma lambda as Lagrangian, which equals to f of x plus summation lambda h of x 1 to L. We call this as Lagrangian function. And the gradient of this Lagrangian function equals to 0. So just to save our time, we just said that this is a Lagrangian function equals to 0. Then we call the lambda, the individual lambdas as Lagrangian multipliers. In multipliers which are basically greater than or equal to 0. Then we have this condition of lambda j star hj x star. So basically for KKT point, this the multiplication of this for each j is 0, and we call this condition as this condition is known as complementary slackness. Condition. And obviously lambda j star is 0 for all j not belonging to the active set of x star. Okay, so I'm sorry if it is bit fast, but just it is just a brief like, so I have to run fast because this is just a brief and a brief overview of optimization, so I have to really go over this fast. However, I'll link all the detailed videos in the description below. So after we actually we came to the derivation and the necessary conditions, KKT necessary conditions, let's see an example basically. Um, to understand how do we actually come up with a to come up with KKT points if we have a optimization problem, constraint optimization problem. So let us take an example. Suppose I have to minimize x1 square plus x2 square, where x1 and x2 are obviously on the real line, subject to the conditions that x1 plus x2 are greater than equal to 1 and x2 is less than equal to 1. So this is my, let us call this as my constraint 1, this is my constraint 2, right? So if I draw this, so x1 plus x2 equals to 1 is this line, and x2 less than 1 is, just use some other color, is this line. Maybe I'll just make the axis with some other color. Let's use green color, which we are using till now. Right, and yeah, this is constraint number 2, and this is constraint number 1, right? So constraint number 1 says that x1 plus x2 is greater than 1. So basically this region, this entire region, and my constraint 2 says that x2 is less than 1. So basically this space, right? So basically in finally the region that is a feasible region is this region. Okay, so let us assume that let us take a point where both the constraints are active. So let us take this point, which is basically 0 comma 1, right? And this 0 comma 1, let us suppose that this is a KKT point, right? So x star equals to 0 comma 1, and my lambda 1 star is also greater than 0, and lambda 2 star is also greater than equal to 0, right? Let's check if this is a KKT point or not. So I'm assuming that it is a KKT point, and let's just verify all these conditions. So if all these conditions are true, then this is a KKT point, otherwise it is not. So I'm assuming that both the uh, constraints are active, and when both the constraints are active, only this particular point remains actually. So 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 we just have x star equals to 1 comma 0. Let's find out the Lagrangian of x star comma lambda star, right, which gives me basically f f is 0 square plus, I'll just write this condition once, x1 square plus x2 square plus lambda times h1 x. So if you notice that in all the conditions hj of x is less than or equal to 0. So let's just convert this particular constraint into this similar form. So if we just invert the inequality, it becomes 1 minus x1 minus x2 less than equal to 0, right? And the second constraint becomes, I just take 1 the other side of the inequality, it becomes x2 minus 1, right? So um, this is my Lagrangian. Let us take the gradient of this Lagrangian. This gives me, so I have to first of all I have to do partial derivative with respect to x1 for the first row. So it becomes twice of x1 minus lambda 1 plus 0, because I don't have any coefficient of x1 here. Then I have 2 of x2 minus lambda 1 minus plus lambda 2, right, and this is equal to 0. And what do I know? I know that uh, x1 is 0 and x2 is 1. So if I put in these values in this particular constraint, I'll get lambda 1 is 0 and lambda 2 is minus 2, which is not possible, because lambda 2 should be greater than or equal to 0. Sorry, it is not x star here. So yeah, since this is not a KKT point, I have to remove the x star from all these cases, right? So now let me assume that um, this constraint, sorry, that so this means that my constraints are like both the constraints are not active. Since lambda 1 is 0, let me just make a guess that let us just assume that only this particular point, this particular constraint is active. That is, my constraint 1 is only active and constraint 2 is not active. So let me assume that, and so what will I do? Case 2, I don't know x, but I know that, and lambda 1 is greater than equal to 0 and lambda 2 is 0 in this case. When, so I'll write this is when both the constraints 1 and 2 are active. This is when only constraint 1 is active. Okay, so but what I know about x is that it follows the, since this is a active constraint, the constraint one is active constraint, x1 plus x2 equals to 1. Okay, so uh, this is what I know. So I'll again write, let's write the Lagrangian, which in this case is x1 square plus x2 square plus lambda 1 1 minus x1 x2 plus 0. Okay, because lambda 2 is 0. And let us take the derivative of this. So twice of x1 minus lambda 1 twice of x2 minus lambda 1 equals to 0. Okay, so this gives me that lambda 1 equals to twice of x1, and sorry, lambda 1 is also equal to twice of x2. This means that x1 equals to x2 equals to lambda 1 by 2. Okay, I just divided by 2. Lambda 1 by 2. Okay, and then let's just plug in this value in this. So what we'll see that x1 plus x2 equals to 1, then lambda 1 by 2 plus lambda 1 by 2 equals to 1. This implies lambda 1 is 1, right? This is true because lambda 1 is always greater than equal to 0 in this case, right? And so it becomes a KKT point because it is following all the KKT conditions. And x1 star equals to x2 star equals to half is my optimal point. Okay, so basically should be somewhere here. So if I want to minimize this particular contour, then half comma half, I'll just half comma half is my optimal point. This is a KKT point. Okay, so yeah, this is how you actually can solve a constraint optimization problem using KKT conditions, and this is what we'll use in the future to solve all the constraint optimization problems, say in case of optimal controls, or even CBF conditions, in a way CBF QP conditions. So we'll consider mostly QPs in this course, and I feel that this KKT condition, first order condition, is sufficient to derive a KKT point, basically an optimal point. Okay, so this concludes our lecture 2, and if you have any doubts or if you have any suggestions, did you like this particular way of me writing on an iPad and uh, showing you the maths, or do you prefer slides? Please mention down in the comments below and let me know if there are any suggestions or if there are any doubts. I'll be happy to solve them. Okay, thank you very much.